Okay, so let's continue. We had left off talking about an introduction to chemical equilibrium, and we're just going to continue with that today. So our upcoming quiz is going to cover up to about a little bit of what we're going to be talking about today, so I'll tell you when the cutoff is. And the first homework assignment will go live today. It's going to be due Monday before the quiz. It's going to be reasonably short, so no worries. So what we mentioned last time was that most chemical transformations, turns out that as the reactants are consumed and the products start to accumulate in the reaction system, the products will then start interacting with each other, and they will start reverting back to the reactants. Now, initially, there's no products, and there's only reactants. So the rate at which reactants are consumed is at its maximum. As they start disappearing, the rate of consumption of the reactant starts going down, because rate depends on interactions, as we're going to see when we talk about kinetics. So the rate of consumption of reactants starts at a maximum and start dwindling down as they get consumed. As the products start appearing, their rate of reaction, which is initially 0 because there's no products, they start reacting, and the rate at which they start reacting and reverting back to the reactant starts increasing. What's ultimately going to happen is that the rate of the reactants transforming themselves into products is going to become one and the same with the rate at which product return back to reactants. And then a steady state, which we refer to as a dynamic steady state, is reached. And at that moment, there's going to be a certain amount of reactants that remains unreacted and will be there perpetually. The same thing happens with products. It reaches a plateau and they don't change anymore. And typically, the full 100% theoretical yield that you calculate for the reaction is not attained, because there will always be a certain amount of reactants present. Now, we call it a dynamic steady state because it's not that the reaction has suddenly ceased. It's that as reactants become products, products become reactants again at a particular rate, which is the same in both directions. And therefore, you will not see any net change in the amounts of reactants versus products. So we've reached a state that we refer to as chemical equilibrium. Now, the extent to which reactions at equilibrium are displaced towards products versus reactants, meaning how much of products actually form, how much of reactants are actually left, that ratio depends on the reaction. For some reactions, they're quite productive, meaning that once chemical equilibrium has been reached, it turns out that most of what's present in the pot are products, and that's a productive reaction. In other cases, it turns out that is the reverse. You mix reactants, and not much happens. There's not much products that are produced at equilibrium. So those reactions are not very productive. Turns out, as we're going to learn, you can do some manipulations to ultimately drive a reaction that is not favorable, that is not productive, towards the production of the desired products by doing certain manipulations that we're going to learn about. But this is the critical concept of chemical equilibrium, which we're introducing it now in a inorganic, non-biochemistry sense. But we're going to be applying all of these concepts once we start talking about biochemical transformations and metabolism and things that happen in the human body, because in fact, pretty much every chemical transformation that happens in the human body is reversible. This is what this means. I mean, it can go back and forth. And depending on the needs of the cell, depending on the needs of the body, depending on what is meant to happen or should happen, reaction can go in either direction. And it is the task of enzymes in the body to decide and drive which direction things are going. So, if you look at in terms of concentration or amounts of substances, so top left, if you start the reaction by mixing pure reactants at time 0, at the beginning all you have is reactants. And then they start getting consumed as time goes by, so this is the red going down, right? Now, of course, at time 0 there's no products, because nothing has happened. But as time goes by, in blue, the products start appearing. And then you're going to reach a moment at which both products and reactants plateau. They don't change anymore. Notice that the reactants have not gone to 0, right? If they were gone to 0, they would be down here. But they're at a certain level, not 0. And the products reach a particular level, whatever it is. And at that point, you can identify the moment in time, sort of around here, just above the T, right? Unfortunately, the pen is giving me grief again today, so I'm going to have to really walk over to somewhere and the IT people, because this is unacceptable that in the classroom we don't have the tools that we need. But anyway, that's my rant of the day. You'll notice if you draw a little line at some point that these are plateauing, right? So that's the moment where chemical equilibrium has been reached. Now, in this particular example, this is a productive reaction, because notice that the blue, which is the products, at the end are present at higher amounts than the reactants. Okay? The alternative, let me turn on the light here so that you can see what I'm writing on the board. The alternative of a less productive reaction would be one, again, amount, and then time is going this way. That one would be something like this, right? If this is reactants, reactants, and then these are products, right? And if you identify it has reached equilibrium, let's say around here, right? Notice that at the end you have more reactants than you have products. So this is less productive, right? All right, what will never happen, or rarely happens, is that the reactants go down to 0, and that the products just go to whatever, right? This is, in most cases, not attainable. So there's always going to be some reactant left, and whatever products form, again, if you have more products than reactants, then that is considered a productive process. Now, turns out, as we're going to see throughout this discussion, that the relative amounts of reactants versus products, or products versus reactants, if I'm pointing to the blue versus red, can actually be influenced by the environmental conditions in which the process is taking place. So in a laboratory setting, we can control temperature, we can control pressure, or any combination of those two. You can manage to drive a reaction or shift it in one direction versus the other. So these are some of the manipulations we can do to drive reactions in the direction that we would like. In the case of the human body, pretty much temperature and pressure are set, right? We're dealing with body temperature, which is 37 Celsius, and pressure for the most part is atmospheric pressure, right? Now, if you look at it in terms of rate, how fast the reactions are going, at time 0, the rate of the forward reaction, which is reactants converting to products, starts at its maximum. The rate of products converting back to reactants starts at 0, because there's no products at the beginning. And as the reaction proceeds and the reactants get consumed, the rate of the reactants converting to products starts going down. As the products appear and accumulate and they start reacting with themselves to go in the reverse direction, the rate of that reaction starts increasing progressively. And then there's going to be a moment at which the rates of forward and reverse reactions are the same. That's when you've reached chemical equilibrium. That's when there's no more net observable change in the concentrations of the substances. So there's a phenomenon, it's a natural phenomenon, that is quite interesting. And this is very generic, but this sort of to illustrate the process. So if you have any random reaction, products A and B producing, reactants A and B producing products C and D, and again, assuming this is balanced, the small letters are the stoichiometric coefficients of each substance. Once this reaction has reached chemical equilibrium, we represent that with a double arrow, meaning it goes forward, but it also goes backward. So it turns out that regardless of how you mix these substances in what ratios, you can mix them in the pot and walk away and come back after whatever time nature has decided that that reaction is going to reach equilibrium. But once equilibrium has been reached, the reaction will adjust the concentrations of the substances such that the ratio that you see here, which is the product of the concentrations of the products, sorry for the redundant term, but product is the mathematical operation, and then products are the product of the reaction, right? The product of the concentrations of the products, each one elevated to its corresponding stoichiometric coefficient, divided by the product of the concentrations of the reactants, each one elevated to its corresponding stoichiometric coefficients, that turns out to be a constant under set environmental conditions of temperature and pressure. So the way you can measure the equilibrium constants of reactions is by, again, mixing substances in whatever ratio you want to start with, walk away, come back, and do this calculation. So the scientific community has done us the favor over the last several centuries to study all sorts of chemical transformations and establish and measure, and there's tables. If you go to Google, you can Google a table. If anybody wants to, go ahead. Table of equilibrium constants, and you're going to get volumes and volumes of equilibrium constants for reactions. So these are important parameters to know when you're studying chemical transformations, particularly in living systems, because chemical reactions under a particular set of conditions have a fixed value of an equilibrium constant. So it doesn't matter what you start with and you mix together, ultimately the reaction is going to shift such that the concentrations of all the species involved are going to be such that they obey this value that is set by nature for whatever reason. Now, one of the things you need to be mindful of in terms of making calculations, mathematical determinations of equilibrium constants of substances, of reactions, is that only substances whose concentrations can change during a chemical transformation are included in the equilibrium constant expression and calculation. So, because if you consider, even if they participate in a reaction, the concentration of a pure solid and liquid, because they're pure substances, they're not in a mixture, their concentrations, how much moles per unit of volume they contain, is invariable. So those are constant values. So those substances are never included when you're putting together the equilibrium constant expression, mathematical expression, and doing calculations using these expressions. So pure solids and liquids are always excluded. Even if they're reacting, their innate concentrations are non-changing. So only gases and substances that are present in a solution as part of a mixture are included in these expressions. So here's an example of a reaction. Let's say hydrochloric acid, which is what in fact makes up stomach acid. Now, aqueous means that it's dissolved. So hydrochloric acid, when it comes into contact or is dissolved in water or interacting with water, it turns out, and this is the topic, in fact, of the 2 chapters from now when we start talking about acids and bases. Whenever a substance like this one dissolves in water or interacts with water, it's going to turn out to transfer a hydrogen atom, hydrogen ion, H+. It transfers that to the water to produce H3O+, which is called hydronium. and what's left from what was the HCl is now chloride. Now, if you're going to put together the equilibrium constant, this is a reversible process. The equilibrium constant expression for this process would involve the concentration of H3O+. So this is a balanced equation, so notice the stoichiometric coefficients for everybody is a 1. Right? So there's one of these, and one of those, and one of those, and one of those. So going back to the expression, it's the products elevated to their coefficients divided by the reactants elevated to their coefficients. Now, the caveat is, if any of these is a pure solid or a pure liquid, those you do not include. Okay? So you'll notice there's a pure liquid in this expression, in this reaction, so it is excluded from the equilibrium constant expression. We only include hydronium, chloride, and HCl. These two on the right are the products, so they're going to go on the top. Concentration of hydronium times concentration of chloride, each one elevated to the power of 1, divided by the concentration of HCl, also to the power of 1. We do not include the water because it's a pure liquid. Okay? So if you're going to write equilibrium constant expressions for reactions, and then I'm going to have to use the board again because of our limitations of technology today. So for the first one, what's the expression? Anyone? So again, KEQ. In the homework, when you get it, this is not going to be in the next homework because it turns out we've already surpassed the point where for the cutoff for the quiz. The quiz only is going to cover, let me just quickly tell you, these concepts. The basic concepts of equilibrium. So this slide and pretty much that slide and perhaps a little bit of this one. But anything involving equilibrium constants is not coming in the next quiz. Just FYI. Okay? All right. So, but just FYI, when you see this in the homework, you may see it as KC because this is the equilibrium constant involving concentrations. Turns out we're not going to talk about it in this course. But if you go take chemistry on North Campus, you'll also learn that you can talk about KP. KP is with gases, when only gases are involved, and you can actually also tabulate equilibrium constants using pressure. Okay, pressure. But we're not going to use that in here. So just FYI, when in the homework you see KC, well, it's our KEQ. Okay, FYI. So for the first one, what would it be? Yes.
In the numerator, like parentheses HI, parentheses 2, but exponential.
Like this?
Yeah.
Yeah.
And then on the denominator, parentheses H, and then a 2, but like down below.
Yeah.
And then parentheses I, and then a 2 in the same fashion.
Okay. Yes. So quick minor correction, it's actually brackets, not parentheses, because brackets has a meaning. Yes. It turns out brackets means molar concentration, which is what it is, right? This is, when we say concentration, it turns out that we're referring to molar concentration or molarity, moles per liter, and that by definition is represented by brackets, okay? All right, so that is correct. The second one, let's just do it right here. So two products, both in solution. Remember, AQ means aqueous. Only one reactant, also aqueous. So pretty much everybody's going to be in this expression. Everybody has a stoichiometric coefficient of 1, right? Because the 2 minus and the plus and the minus, those are charges that are part of the structure. So everybody has one stoichiometric coefficient. So HPO4 2 minus times H plus divided by concentration of H2PO4 minus. Yes? And then the last one would be, yes? Okay. KCl. Okay, I was going to do it, but I was going to let you figure it out. Yeah.
So the only one that would be out would be O2.
Yeah. O2. And that's it, cubed. So O2 to the 3, and that's it. You do not include the KCl nor the KClO3. Yes?
So you wouldn't just put it like over 1 since there's
It's well over 1, it's the same thing. Yeah. So only the species that are gas or aqueous. No solids, no liquids. Yes? All right. So the value of the equilibrium constant for a reaction, as I've already mentioned, is a constant. It's invariable under a given set of pressure and temperature conditions. So when you are working with these types of calculations, the concentrations of the substances will be always adjusting themselves such that when you're entering these concentration values into the expression, these expressions that we've talked about, right, they will produce the same value. Now, there has to be some of all species present in the reaction, because otherwise it's not going to work. But this is the key point here. Regardless of what you started with, this is what I've been saying, you can mix reactants or even products or any combination of reactants and products in any ratio that you want. Mix them in there, close the pot, walk away. They will all adjust themselves naturally to reach whatever concentration values they have to, such that when you put those values, once equilibrium has been reached, if you were to then measure how much of each substance is present, and you put those numbers into the equilibrium constant expression, as long as there's at least a little bit of all of them in there, they will all ultimately produce concentrations that if you put the numbers into the equation, you're going to get the constant. This is a natural phenomenon. Okay? So all you need to do to determine KEQ for a reaction is mix reactants and or products in whatever ratio, close the pot, walk away, and then come back once equilibrium has been reached, take a sample, figure out how much of substance A, how much of substance B, how much of substance C, etc. Put the numbers into the equation. Oh, sorry, my thing is... Put the numbers into this, and that's how you determine the equilibrium constant. Okay? All right, so this is what the scientific community has done for us over the last several centuries. So we're going to use an example. We're going to use an example to guide us to illustrate these concepts. So this is obviously not a biological transformation, but the same that we're going to see and illustrate with this simple example applies to any biochemical or any transformation in general. So this reaction, which is called the Haber process, I'm going to shut this down so you can see better until we need to go back to the board, is actually a very important reaction in industry that produces ammonia. So ammonia is a very important substance in all sorts of places. But one of the major uses of ammonia is used as a source of nitrogen, as a starting material for making fertilizers for all kinds of crops and all kinds of things that if we didn't have them, we wouldn't be having this conversation, right? So ammonia can actually be made from its constituent elements, hydrogen and nitrogen. They're all gases, it turns out. So let's say you're running a reaction of this transformation in a laboratory, small scale, because these things are done in the ton amounts in industry. Right? When you're going in the lab, you're doing it in a small reaction, small scale. So let's say you mix half a mole of ammonia and half a mole of hydrogen You put them in a 2.5 liter vessel at constant temperature and pressure. And then once equilibrium is reached, it turns out that you take a sample and 0.390 moles of ammonia were found to be present. Now, if you analyze what's happening, what have you added to this pot? You've added ammonia, which is the product, and you've added hydrogen, which is one of the reactants. So what is not there? Nitrogen is not there. So then some nitrogen needs to form in order to ultimately reach equilibrium. So what that means is that some of the ammonia has to be consumed, and the reaction is going to go backward, to then, at the expense of the ammonia, some nitrogen is going to be produced, and of course additional hydrogen will be produced on top of the half a mole of hydrogen that's in there. So to then determine, you can determine what the equilibrium constant is by doing a little bit of math. So this is what we need to realize. The equilibrium concentrations of all species initially can be calculated as shown here. So we have a half a mole of ammonia. The volume of the vessel is 2.5 liters, so we have 0.2 molar ammonia. The same thing applies for hydrogen because we mix the same amounts, right? 0.2 molar. Initially we have 0 nitrogen, none. Now, we already know that the final concentration of ammonia is 0.390 moles, right? This is the number of moles that are measured. And it's in the same vessel because it's all in a closed container. So the concentration of ammonia, once equilibrium has been reached, is 0.156. Now, we can use all of this information to then determine how the different substances changed, how much nitrogen will have been formed, to then calculate what is the equilibrium constant for the reaction. So what you need to be mindful of is the stoichiometry of the reaction, because things will change honoring the stoichiometry of the reaction. So again, we call this an ice table because we're going to start with an initial a set of conditions. There's going to be a change that we've already established there's a change because the ammonia changes from half a mole to 0.39 moles, right? And then there's going to be an equilibrium condition. So this is what you have to be very careful in terms of establishing. So we've already established by the conversation that we had that because we start with no nitrogen, ammonia has to go down. Some of it has to be consumed to produce nitrogen. So if you look carefully at the stoichiometric coefficients, if X is the amount of nitrogen that is produced, we call it plus X. We don't know what X is, that's what we're going to figure out. For every X that appears, because its stoichiometric coefficient is 1, that means that 2X, 2 because it's double, right? Notice, for every one of these, there's 2 of these. So if we say plus X for this one, that means that double of X must have disappeared of the ammonia, okay? Because they're in a 2-to-1 stoichiometric ratio. But then that also means that because hydrogen is 3 times the number of moles of nitrogen, for every X that appears, 3X of hydrogen, have appeared. Yes? So once equilibrium is reached, we're going to have X of nitrogen, which is what we're going to try to figure out. We started with 0.2 molar ammonia. It went down by 2X, if X is what appears of nitrogen. And then we started with 0.2 of hydrogen, but 3X will have been added to that. So now we have a variable that we need to figure out what it is. Well, luckily, we already know, because we've been given this information, that at equilibrium, the concentration of ammonia is 0.156. We know that because we ended up with 0.39 moles in a 2.5 liter vessel. So what does that mean? What that means is that this number down here, 0.2 minus 2x, equals 0.156. Because that's what we have at equilibrium, right? So this is the same table that was on the previous slide. The unknown value of X can be determined from the measured change in the concentration of ammonia. So we started with 0.2. We've established that for X to appear of nitrogen, 2X of ammonia have to have been lost. So that difference is what's left, which is 0.156. So this is just a simple algebra calculation. You're solving for X. X equals 0.022 molar. That's the value of X. So then, what does that mean? Well, we already know ammonia ends up being 0.156, because we've established that from the data that we were provided. Now our task is to determine how much nitrogen and how much hydrogen is in the pot. So we've already established that X equals the concentration of nitrogen. So this actually is the concentration of nitrogen. How much hydrogen is going to be left at or present at equilibrium? Well, we started at 0.2. We added 3x, because for every x that is produced, 3x of this one are produced. So we've already established how much x is. 0.2 plus 3x, so 0.2 plus 3 times this. This is how much nitrogen is present at equilibrium. So ammonia went down from 0.2 to 0.156. Nitrogen, of which there was none, went from 0 to 0.022. Hydrogen went from the initial 0.2, it increased to 0.266. So now you can take these numbers that you have experimentally determined and put them into what would be the equilibrium constant expression. In the case of this reaction as you see it, everything is a gas, so they're all participating in the equilibrium constant expression. Ammonia squared divided by hydrogen cubed times nitrogen. So you pull the numbers, right? 0.156, 0.022, 0.266 for the three different substances. So ammonia is 0.156 squared divided by concentration of hydrogen, which is 0.266 cubed, times the concentration of the nitrogen. So the equilibrium constant under these conditions, whatever they were, temperature, pressure, turns out to be 59. Okay? Yes?
Why do the brackets change to parentheses?
Oh, because these are just numbers at this point, right? So so the values can be put in parentheses, but then when we're talking about the actual concentrations, the brackets mean concentration. Okay? Everybody's with me? So this is how, over the past several hundred years, people who have studied chemical reactions, they just mix stuff, close it, walk away, come back, measure. How much of this? How much of that? And then you can actually measure all of them, it turns out. And then just do the calculation. But all you need to really measure is one of them. And then you can do the math to figure out the rest. This is what we've done here to illustrate the process. The reason why we're showing you the whole process, because this is the critical piece that you need to understand, is the stoichiometry, right? So it's a 3:1:2 ratio. So you always have to adjust the pluses and the minuses, and you have to ensure that each variable will have always in front of it the corresponding stoichiometric coefficient, because any change in any one of them has to be corrected for the other one by using the stoichiometry. Yes?
So why is it the change on ammonia is -2?
Because we start with 0 nitrogen. There's none. So some has to be produced in order for the reaction to have reached equilibrium, because there has to be some of everything, right? So the only way that you can make nitrogen is if ammonia decomposes and produces some nitrogen, and then of course a little bit more hydrogen, right? In other cases, it's depending on the initial situation, it can be completely different. You may have to have these disappear and that one appear. It depends on the initial conditions, okay? All right. So, as I've said, the value of an equilibrium constant is a constant, as the term implies, but it is constant at a given set of conditions. So temperature and pressure need to be set. If you change temperature and or pressure, turns out the equilibrium constant changes because the reaction changes its direction. You can manipulate which side is favored, which side there will be more of, products or reactants, by changing temperature and pressure, it turns out. Okay? So these are manipulations that we can do to do that. So if we want to increase this equilibrium constant, we're going to go through some examples. But the only way you can change this value is by changing the temperature and or pressure at which this reaction is taking place. So if you want to increase the number, increasing the number implies more ammonia is present and less of the reactants. So if the goal is to make ammonia, you could change the conditions such that it shifts towards the ammonia. Of course, that would cause the equilibrium constant to go up. And that's typically what you would want in the Haber process to make ammonia, right? So we're going to talk about that, how can you can manipulate conditions to drive the reaction where you want it to go. But this is a critical point. The magnitude, the size of that number, is reflective of what side of the reaction is actually favored in that process. So when you have a very large equilibrium constant, what that means is that there's going to be an abundance of products over reactants. Because if you recall the expression of the equilibrium constant, it's the product of the products divided by the product of the reactants. So if you have lots and lots of products in that reaction at equilibrium, what does that mean? That the top of this is large and the bottom is small, right? And if you have a large numerator and a small denominator, the number is big, right? So if there's lots of products at equilibrium, which is a productive reaction like the one we see here, those are going to have large equilibrium constants because there's going to be lots of product, not much reactant. If you have a reaction that has a small equilibrium constant, then that is not a productive reaction. Because what that means is that at equilibrium, once equilibrium has been reached, it turns out that most of the reactants remain, and there's not much products in the pot. So the numerator of that expression is small, the denominator is large. Something small divided by something large makes it even smaller, right? Now, what that truly means, if you have a large equilibrium constant, meaning lots of products are present, they're more abundant, that truly translates to that the products are more stable than the reactants. So nature drives it in that direction because nature always goes towards stability, as we're going to learn when we talk about thermodynamics. Okay? If the reaction has a small equilibrium constant and therefore the reactants are present in greater amount at equilibrium, that means that turns out the reactants are more stable than the products. So nature does not want to go in that direction. Okay? Now, of course, we try to go against nature in many situations in life, right? And we can actually drive things in the direction that nature doesn't want you to go. Yes?
What makes the equilibrium large versus small?
The constant?
Yeah.
It's a natural phenomenon.
But like,
It's per reaction.
but like number-wise? Like
Number-wise. So, what makes it, so typically, it depends on the reaction, but when you, numbers greater than 100, let's say,
Yeah.
those are, or 1,000, those are large equilibrium constants, yeah. And then when they're really fractional, like 0.1, 0.01 or smaller, those are very small, yeah. Everybody with me? We are on our usual channel 70. Okay? All right. So we need to describe a situation in which when you're looking at a reaction that is actually ongoing and hasn't reached equilibrium. And then we're going to reach the point of describing what, in my opinion, is one of the most important principles in the entire field of chemistry. And I would say if you're going to walk away with one from this entire year-long course, it's Le Chatelier's principle, what it should be. Okay? We'll talk about that. So we've established that if you add substances that are going to be reacting to a reaction vessel, you close it, you walk away, and you wait long enough for it to reach equilibrium, when things are no longer changing in terms of concentrations, you can establish what the equilibrium constant is by measuring those concentrations and putting them into the expression. But how do you know? Let's say you've reached that point, the equilibrium constant has been established, and this is what has been going on for the last several hundred years. So that information is now public. It's in the public domain. You know what the equilibrium constant for every reaction you ever want to carry is. It's out there. So let's say you're in the lab, and you're carrying out a chemical transformation, and you don't know that you've waited long enough for the reaction to have reached equilibrium. So you're making measurements, and you're trying to establish whether you have reached equilibrium or not. And you take your sample, and you measure how much you have, and you put the numbers that you've calculated into the equilibrium constant expression, but you don't get the value of the equilibrium constant. What does that mean? You've not reached equilibrium yet. Now, the magnitude of the number that you get in that situation where you're still in between will tell you where you are. If the reaction is actually moving forward or if it's actually moving backward. We saw in that example with the ammonia and the nitrogen that initial moment, when you put the half a mole of this and the half a mole of that in the pot, the reaction needed to go backward to make nitrogen from the ammonia. Okay? So how do you establish which direction the reaction is going? So this random calculation of concentrations that you plug into the equilibrium constant expression and the number that you get at that snapshot or instant in time is what we call the reaction quotient. Because it's the value that you get at any random moment. That is not necessarily when the reaction has already reached equilibrium. So the magnitude of that value, as I've said, relative to the KEQ that is known and established, tells you what direction the reaction is going. So if the product concentration at that random moment is greater than what it should be at equilibrium, that means that there's too many products in that pot, so the reactions are the deficit. The reactants are the deficit. So if you calculate Q, you're going to have more products than you should, meaning there's less reactants than there should. Q is going to be greater than K. So what that means is that the reactants must go up, the products must be consumed, the reaction has to move towards the left, from products towards reactants. So the products have to decrease, the reactants have to increase. Ultimately, the Q is going to become K. If you go to your reaction and you take your sample and you put the numbers and the number you measure equals K, then what does that mean? You've reached equilibrium. You're there. It's done, right? But if it's not K, then you either are higher than K or lower than K. If Q is larger than K, Q has to go down. How does it go down? Well, the products need to be consumed. The products need to be produced. The reactants need to be produced. So let me say that again. If Q is greater than K, then the numerator top number needs to go down. Right? Products need to be consumed. The denominator, which is the bottom, needs to go up. Reactants need to be produced. The reaction needs to go backward. What if you get the opposite situation? If your reactants at that random moment are more than what they should be at equilibrium, then you have too many reactants, you've not yet formed enough products to reach equilibrium. Q is going to be less than K. So that means that your reaction at that moment that you've taken your sample is actually moving to the right from reactants towards products. The reactants have to be consumed, more products need to be produced, and ultimately Q becomes K. So here's sort of a summary of what I said. Reactions will always be shifting in the direction that brings them to chemical equilibrium. The relative ratio of products to reactants establishes if they've reached a... Yes, question.
Is Q the same formula as K?
Exactly the same formula as K. The difference is that the numbers that you put in Q are what you take at any random moment. K is K, right? So the magnitude you get at that random moment tells you, where is this going? Well, if my Q is greater than K, the number needs to go down. So products need to go down, reactants need to go up, right? That's what happens here, right? If your products are too much than what they should be, Q is greater than K, this needs to go down. The only way that it goes down is by reducing the products and making more reactants, right? The reaction is going towards the left. If the opposite is true, if at the moment you make your sample, you observe that your Q that you measure is less than K, well, what does that mean? Well, I have too many reactants, I need to make more products. The reaction is going to be actually shifting towards products at that moment that you're making your measurement. Ultimately, Q will progressively change until it becomes K. Once it becomes K, the reaction has reached equilibrium. Okay? So this is simply a little way to gauge. Q is a way to gauge where is my reaction. Okay? It's a measurement at any random moment in time. It's the same. Ratio of products over reactants elevated to the corresponding coefficients. If Q is too large, it needs to come down, right? That's what's over here on the left. If it's too big, it needs to come down. How does it come down? Products need to be consumed. Reactants need to be produced. Reaction is actually moving backward, right? If you're measuring your Q, which is what would be the typical situation, you're mixing the reactants. You want to know if it's reached equilibrium. So you're sampling over time. If you've not yet reached equilibrium, your Q will be less than K. It's not there yet. So more reactants need to disappear, more products need to appear. But it really depends on how you started the whole thing. Okay? Ultimately, once Q becomes K, then you're at equilibrium. Okay? So let's illustrate these processes, these concepts, with some examples. Back to the Haber reaction. So let's say now you mix in a pot half a mole of each of the three substances of the reaction. Okay? And you want to know, where is it going to go? Is it going to make more ammonia? Or is it going to go backward and consume ammonia and produce nitrogen and hydrogen? You need to be able to know that, right? So, because they all have the same amounts in the same container, all of them have the same initial concentration. So half a mole and 2.5 liters, it's 0.2 molar. So now I want to know what's going to happen here. So how am I going to know that? Well, let's figure out what Q is at that instant where things are starting. Well, they're all 0.2 molar. This is the equilibrium constant expression, right? So 0.2 squared for ammonia, 0.2 cubed for hydrogen, 0.2 for nitrogen. You do this math, 25. Less than Q, less than K. So Q has to increase to get to K. How does that happen? The only way that happens is if you make more ammonia and you consume hydrogen and nitrogen. It has to shift to the right. So under these conditions, the reaction will shift towards products. It must, because ultimately the concentrations of all of the substances, once you put the numbers in, it has to equal 59, because that's what nature has established. So more ammonia will be produced from the available hydrogen and nitrogen, and of course some of the hydrogen and nitrogen has to be consumed, right? So we can set up the math. Again, we're not going to bore you with the whole process of the ice table, because that's actually a complicated process for this particular reaction that has squares and cubes and all kinds of things. So using ice tables with the +2, -2, whatever, plus x, minus x, whatever that is, it turns out that you can then establish that at equilibrium, after doing your measurements, hydrogen has reached a concentration of 0.165. Nitrogen has reached a concentration of 0.188. So notice these two have gone down, which is what we predicted, right? And then ammonia has gone up to 0.223. If you put the numbers in here, this is what you get. So this is a natural phenomenon. Doesn't matter what you put in of the substances, they will figure it out, and they're going to go in the direction they need to, such that under the set of conditions of temperature and pressure, the concentrations will adjust themselves. Regardless of initial conditions, substances will react to obey the reaction's equilibrium constant. They're going to adjust themselves. Okay? So this is what happened, right? We started with 0.2 of each substance. This is this second set of conditions, right? And then close the pot, walk away. We know already from calculating Q, it was less than 59, Q was 25. It has to shift towards more ammonia. At equilibrium, more ammonia, and then of course less of the other two, right? So to that pot, to that same pot, I'm going to add a little bit more nitrogen, only nitrogen, to see what's going to happen. So there's a sudden increase in the nitrogen concentration. That causes a disruption in the equilibrium. Well, the system is going to respond to that disruption to reestablish the equilibrium as it needs to be, such that all of the concentrations will adjust themselves to obey the equilibrium constant for the reaction. That's the gist of Le Chatelier's principle, it turns out. Right? The Chatelier's principle says, in more qualitative terms, whenever a reaction at equilibrium is disrupted or subjected to some kind of stress or intervention or change, the reaction will respond accordingly to restore the equilibrium and bring everything back to what it needs to be. So, at that moment that you add the half a mole of nitrogen, which is one of the reactants, we haven't added any hydrogen, so that's not changing. We haven't added any ammonia, that's not changing. But we had, at that moment, 0.188 of nitrogen. We're now adding a little bit more nitrogen. Half a mole in the same container, so it's 2.5 liters. This is the concentration. When you add that to that, suddenly that concentration goes up to 0.388. What's going to happen? Well, if you do the numbers, this is what we started with ammonia. This is what we start with hydrogen. And now, all of a sudden, the nitrogen is 0.388. So now that produces a Q of 28.5. So what does that mean? It's going to shift to the right again. It's going to make more ammonia at the expense of the hydrogen that's present, and in fact some of the of the nitrogen that's there, including what was added, some of it will be consumed as well, because we need to shift to the right. So some of the added nitrogen plus some of the existing hydrogen will be consumed, more ammonia will be produced. Until when? When does it cease moving to the right? Until Q equals K, right? So you can do the math. It turns out, we're giving you the answer to the math. If you go in the textbook, you're going to see the entire thing. But just for the sake of time and to alleviate you the complexity. And you're not going to be responsible for learning and telling us on an exam or quiz how we get to these numbers. We're just giving you the numbers. Again, the textbook illustrates it as an FYI. This is what you end up with. Hydrogen, notice it went down further, right? Because it was 0.165. The 0.388 that suddenly appeared after adding the additional half mole goes down to 0.379. The ammonia is produced even more from 0.223. It goes up to 0.241. If you put the numbers in this new system of equilibrium, 59 again. So it's a natural phenomenon. You don't have to do anything. So this is, again, what I was saying, disrupting a system at equilibrium, shifts the reaction so that the reaction's equilibrium constant is obeyed by all substances and restores the chemical equilibrium. Okay? So, again, here, this is the sudden change. Notice it went up to 0.388. Well, then this is the final equilibrium, right? This goes down even further. This goes down a little bit, and this one goes up even more. And if you put these numbers into the equilibrium constant expression, you're going to get the 59. So, again, the key principle that these examples illustrate is that disruption of a system at equilibrium causes it to respond in a manner that counterbalances that disruption or perturbation until equilibrium is reestablished. So if you add a reactant, what that is going to cause is that some of the reactants will need to be consumed to bring the reaction towards products, because you've disrupted by increasing the amounts on the left. The system wants to decrease the amounts on the left. Well, the only thing that can happen is if it moves to the right, okay, to make more products. If you remove products, you can do any maneuver. If you remove products, what happens? Well, suddenly the products have gone down. So how does the reaction respond? It wants to make more products. So what that means is that some of the reactants will be consumed. That ultimately leads to the production of more products in an attempt to restore the equilibrium. If a reactant is removed or a product is added, so you remove something from the left or you add something on the right, either of those two is going to cause the reaction to shift to the left. Because removing a reactant, suddenly the reactants have gone down, they need to be replenished or restored, system moves to the left. Products are consumed, more reactants are produced. If you add a product, has the same effect. You're adding product, system wants to reduce the number of products, so it moves to the left in order to do that. So it responds in accord to whatever is done. Now the second one in the middle is the one that's critically important, and that's the one that's the most useful. When you have a chemical reaction whose equilibrium constant is small, meaning not much products are going to be produced. Well, if you manage to fish out the products, even if you get a small amount, if you fish them out and isolate them from the rest, well, what have you done? You've isolated your product. You've perturbed the equilibrium by removing a product. How is the reaction going to respond? It's going to make more product. Well, if you continuously remove the product and remove the product and remove the product, you've managed to isolate that product. Yes?
But then will the product not on its own then become parts of the reactants?
Depending on the conditions, it may, but if that product is removed and is then immediately consumed in a third transformation, then it's gone forever. So good observation. Technically, the product by itself should revert back. So the reason why we bring this particular one up is that this is what actually happens in many biochemical transformations, in which they are multi-step. So a reaction is not very productive, but that smidgen of product that's produced is the reactant for the next step. That smidgen that's produced, taken away. So done. The process works through these equilibrium processes. Okay? All right. So yes, sometimes to actually technically fully isolate that product, you need to somehow further transform it in order to be able to say that you've consumed, that you've isolated it. So this is Le Chatelier's principle, right? So reactions at chemical equilibrium. I don't know what this is about, but anyway, I think you should say will respond. There's a typo there. Reactions at chemical equilibrium will respond at WIL, will respond to a perturbation by shifting in the direction that counterbalances the effects of that perturbation and returns the system to chemical equilibrium. Okay? Yes?
Is this like a negative feedback homeostatic?
It's a homeostatic mechanism. Negative feedback has particular implications, but it's technically, yeah, the system is sort of self-analyzing that something has happened on one side, and yes, it tries to, restore whatever change has been made on that side by counterbalancing the effects of that change. Okay? we're going to talk about positive and negative feedback when we talk about biochemistry. It's a little bit different context, but I see where you're going. All right. So, speaking in terms of equilibrium constant expressions and concentrations, a system at equilibrium will respond to that perturbation by bringing the concentrations of all of the substances to new values that when you put them into the expression, they're going to still obey the value of the equilibrium constant as we've already established with the examples that we saw. So this fundamental principle, as I've said, this governs everything in chemistry. It's all about Le Chatelier's principle. And most notoriously in biochemistry, as I was alluding to earlier, many things are happening, multi-step reactions. They all have their own equilibrium constants, so certain ratio of products and reactants, but then things are happening in tandem that ultimately allows things to happen as they should. Okay? All right. So this reaction here is a very important reaction that we're going to study in a little bit more detail later. It's important in acid-base balance in the human body. So again, CO2 produced by your cells as you sit here listening to this discussion, all metabolism in your cells that are consuming nutrients to produce energy ultimately produce large amounts of CO2. A portion of that CO2, in fact the largest portion of that CO2, ends up chemically reacting with water to produce carbonic acid. This is a perfectly reversible process. And again, that carbonic acid further decomposes to protons and bicarbonate. This ends up being the carrier of CO2 in blood. Notice how technically the carbon of the CO2 is incorporated into this. Right? This is very water soluble because it's an ion, as opposed to CO2, which has very little water solubility. So the body undergoes this transformation in order to be able to transport large amounts of CO2 masked in the form of bicarbonate throughout the body, and then a portion of it goes into the kidneys, and then because of the total reversibility of this process, in the lungs, CO2 gets exhaled. So again, it says predict the response of this equilibrium and its ultimate effect on how much acid when CO2 is retained due to lung disease or when bicarbonate is lost in the urine due to kidney disease. So let's say you have some lung problem, you have COPD or some kind of situation in your lungs that you're retaining too much CO2. So how is that going to affect your H+? H+ is your acid content. Okay? So you're not breathing right, you have problems with your gas exchange in your lungs, you're retaining CO2. Too much CO2. What happens? Well, if you have too much of something that's a reactant, suddenly this starts to go up for whatever pathology you're going on. What is that going to do? It's going to shift the reaction to the right in response, right? Because suddenly one of the reactants starts to go up. Well, the response is it's going to shift this equilibrium to the right. So then what that does is that then it increases the amount of acid. This is what we call a respiratory acidosis. It's the direct result of too much CO2, right? Now, if you're losing bicarbonate in the urine because you have some kidney problem that you're not able to recover, reabsorb, retain bicarbonate, what's happening? Well, now you're losing one of the products of this reaction. So a product is disappearing. So what happens? It's going to try to replenish the product, right? So it's going to move to the right as well. So the acid goes up as well. So loss of bicarbonate is a metabolic, leads to a metabolic acidosis because it by mere shifting of the process to the right, it causes increase in the amount of acid. So we're going to talk about this later when we talk about acids and bases. But these are daily routine issues happening with patients that are in the hospital. So again, when those of you who are going to be taking care of patients in a hospital setting, this is bread and butter. Patient has an acidosis or an alkalosis because it really depends on what's happening. We're going to see all scenarios later when we talk about acids and bases and the physiology of all that. But it all is governed by Le Chatelier's principle. Now, CO2 is under the control of the lungs. Bicarbonate is under control of the kidneys. They work together to ultimately So if suddenly there's too much loss of bicarbonate that leads to a shift of this to the right, how do we shift it back to the left? So we have a metabolic acidosis. Well then, if you breathe, you have increased rate of breathing and increased depth of breathing that causes loss of CO2. So now, this one has been lost, will cause it to shift to the right, but if at the same time, or shortly thereafter, CO2 is simultaneously lost, then it shifts back to the left. Ultimately, what that does, it brings the H plus back to normal. So a metabolic acidosis is then counterbalanced by a compensatory respiratory alkalosis, right? And then that tends to help, it doesn't always work, help balance these things out. Where this becomes a critically important situation is when you're working with patients who are in the ICU, who are hooked up to a respirator. And again, based on their urine bicarbonate and their blood bicarbonate and their blood acid content, then you have to make adjustments. This is daily, that needs to happen with these patients. Adjust their rate of respiration, how much this, how much that on the machine, such that, again, the acid-base balance is maintained. So it's important information that you're going to be using in the real world. All right. So this is what I said earlier. Le Chatelier's principles then is what allows us to externally manipulate reversible reactions. As I've said, many chemical transformations have small equilibrium constants. They're not productive, meaning reactants predominate. So one way to drive them to produce more product, I've already talked about removing products as they form. You can also use an excess of one of the reactants, and that disproportionate amount of one of the reactants sort of tilts the balance towards the formation of the products, and you can ultimately obtain that product and use it to whatever it is that you're going to do, right? So physiology, i.e. biochemistry, exploits this very important phenomenon. Again, some substances are provided in abundance in certain biochemical transformations, in which the abundance of that one substance helps drive a reaction that it is ultimately involved in. And as I mentioned earlier, shuttling substances, as they're produced, just shuttle it in another direction, consume it, and use it in the next step, and that will ultimately drive the whole process in that direction. All right. Everybody still with me? Okay. So I mentioned how under a given set of experimental conditions of temperature and pressure, the equilibrium constant of a reaction is what it is. It's a constant value, but if you change the conditions on which the reaction is taking place, the position of the reaction, meaning whether it's leaning towards reactants or products, can be affected. And once you reach that new set of new conditions, new temperature and or new pressure, a new equilibrium will be established with a new equilibrium constant. If the KEQ goes up, that means the reaction has shifted towards products in the process. If it goes down, then it's actually shifted towards reactants. Okay? So, changes in temperature will cause a reaction to shift depending on whether the reaction is endothermic or exothermic. So let's define what that means. Endothermic reactions, by definition, are reactions that absorb heat as they are progressing. So, because heat is being absorbed, you can consider heat a reactant of the process. Okay? Because it's consumed. Heat is needed for these processes to happen. So if heat is a reactant, increasing the temperature is the equivalent of adding a reactant, adding more of a reactant to the pot. So therefore, the reaction responds by shifting to the right towards making more products. So if you have a reaction that you know is endothermic, one way to maximize product yield is to do it at high temperature, because that's going to drive it to the right. If you cool the reaction, then it has the exact opposite effect. If you turn down the temperature, then technically you're removing a reactant. And how does the system respond per Le Chatelier's principle? If you remove a reactant, the reaction shifts to make more reactants. It shifts to the left. So less product is produced. So the exact opposite is the case for exothermic. Exothermic means that the reaction actually produces heat. So in these types of reactions, as you're going to learn in the lab, when you actually mix things together, and if you put your hands on the container, or if you have a thermometer, it gets warm because heat is being released. Right? So the exact opposite happens in an exothermic reaction. So heating these reactions, technically you're adding a product because heat is produced as part of the product. So that's going to cause it to shift to the left towards reactants. Cooling an exothermic reaction actually causes it to shift to products because you're now removing a product that causes it to shift in that direction. So the consequence of these manipulations is that it turns out that the magnitude of the equilibrium constant is temperature dependent. And that depends on whether the reaction is endo or exothermic. So while the K is constant at a given temperature, changing the temperature shifts the reaction in one direction or the other depending on whether it's endo or exo. That changes the position of the equilibrium. That changes the value of the equilibrium constant. So again, if you have an endothermic process, increasing the temperature causes it to shift to the right. So that causes KEQ to go up. The equilibrium constant increases. Cooling does the exact opposite. It brings everything to the left, and if you walk away, lower the temperature, walk away, and come back, and you measure the concentrations, you would have gained reactants, lost products, the KEQ has gone down. The exact opposite happens with an exothermic reaction. If you increase the temperature, you lose products, gain reactants, KEQ goes down. If you cool it, reaction moves to the right because you're removing a product, which is the heat. KEQ ends up going up. Okay? All right, so because this is a reasonably long discussion, and I think we have like another minute or two, I'm going to stop there for today. So stay tuned for your email because homework assignment is going to go up very, very soon, and it's going to be due on Monday.